Thank you. So this is the second part of the talk. So in the first part, I explained how we can analyze the complexity of solving an algebraic system of equation and what we expect from a good algebraic modeling for application. And today I will present you an application to cryptography, and in particular cryptography with coding theory. So I will first recall a little bit what is coding theory and how we can do cryptography with codes. So, but it will be short. So what is a linear code is just a subvector space of a vector space. So I take a vector space of length n over a finite field fq, and a linear code is just a vector space of dimension k in this fq to the n. So we can describe the vector space with a generator matrix that will have rank k, or with what is called the parity check matrix, which is a matrix describing the kernel of this matrix, and in fact it describes what is called the dual code of a code. So talking about the code of or the dual is exactly the same. And in coding theory we have a vector space equipped with a distance, a metric, and we look at the distance between points in the vector space. And what can we do when we have that? We can compute some parameters, in particular the minimal distance of a linear code, which is the minimal distance between two code words. And if we know the minimal distance and we look at a ball of radius some r that will be less than d minus 1 over 2, then it's clear that two different balls do not intersect. And if you have a point in the vector, in the space, in the ambient space, that is at distance less than r from the code, then you can recover the only code word that is the closest code word from this point. And this is the idea of error correction. You send a word that is a point in your vector space. You get some errors that are not too large, and then you can recover the point that you sent at the beginning by taking the closest code word. And so how can we do cryptography with an error correcting code? The first crypto system like that was the Magali crypto system. It was invented at the same time as the RSA crypto system that is used everywhere today, but it has not been used until now because of some problems like the large size of the public key. And how do you do cryptography with an error correcting code? The public key is just a code, and you describe the public key with the generator matrix or the parity check matrix. You take the smallest one to describe the code. And so this is public, and also the correction capacity is public. So it's just a value. What is the private key? It's just an efficient decoding algorithm, a polynomial time decoding algorithm of your code. And if you take a random code, so a random code is just a random generator matrix, it's hard to decode. The decoding problem is a hard problem. So to design a good crypto system, you need to start from a family of codes that you can decode efficiently, and then change your public key to provide to the user the public key from which it's hard to get an efficient decoding algorithm. And so the security is based on the fact that given the public key, you cannot recover the decoding algorithm. And then to encrypt a message, you just take at random a message. You encode your message in your code. This is an element of the vector space. And then you select at random an error, and you add an error to the message. And then you get a ciphertext, and if you want to recover the message, you need to compute the error. So if you have the private key, you know how to decode, so you can recover the error and then recover your message. And if you don't know the private key, you are not able to recover the error. So this is the idea. Yes? Yes. This is just take the uniform distribution. So you take an element in FQ, a vector of length n over FQ uniformly. I will just use the uniform distribution in all the talk. Okay. So some remark, if I give you a public matrix and y, and I ask you to find E such that y is equal to xj plus E, it's easy, it's just linear algebra. Everyone can do that. What is hard is to find E with the weight constraint. Okay? This is the hard part. And there is this equivalent formulation with the parity check matrix. So in this setting, the message will be encoded in the error. It's a different way of doing it. So you take the error, you apply the parity check matrix, and you get what is called a syndrome. And recovering the error from the syndrome, it's equivalent to recovering the code word from the message. It's the same. So we usually talk about the Magali cryptosystem, which is in fact this Niederreiter cryptosystem with the parity check matrix. But both are exactly the same. So one is called the decoding problem, and the other one is the syndrome decoding problem, and they are equivalent. And usually the distance we take for error correcting code is the Hamming distance, where the weight of a code word is the number of non-zero positions in the vector, or the distance between two code words or two words is the number of different positions between the two vectors. But today we will use another one that I will describe after. I described an encryption scheme, how you can encrypt a message, and it's also possible to do signature schemes with coding theory. So if I want to design a signature scheme, what we can do is take as a private key a random error with some weight R. And the public key will be a random matrix. And what is interesting is in this setting is that I don't need a decoding algorithm. I just take a random code, and I know that for a random code, no one knows the decoding algorithm. So for the Magali cryptosystem, you have this trapdoor. That is, if you know the decoding algorithm, then you can recover the clear text. Here we do signature schemes with only random instances, and this motivates the analysis of random decoding. So the public key is a random matrix, the private key is a random error, and we publish the syndrome of this error under this parity check matrix. And then we design what is called the zero knowledge proof of knowledge, which is a protocol where you prove to a verifier that you know the secret. So you have this, you know this vector of small weight, and you prove to someone that you know the vector, but the proof is done without revealing anything on the error. And I will not describe exactly how it can work, but the idea is you can, for instance, change your problem with the permutation and reveal the permutation, the permuted vector of your error. And if you reveal a permuted version of your vector, then you reveal nothing on your error, just knowing how many ones you have in the vector. But you can prove that you know the error. It's possible to design such a proof of knowledge. And this is what is called an interactive proof of knowledge, where first the prover commits to some values, then the verifier asks one random value, and then you reveal something from the initial values. So you commit to so maybe I will show you just after. Just to finish that, so it's interactive, and the security is based on the fact that you take values at random to ask the prover to prove part of a problem. And the prover cannot know in advance which part he will be asked to prove, so he has to provide the proof for all the parts. And if he can prove all the parts, then he knows the secret. So, and there is this Fiat-Shamir transform where you can start from a proof, an interactive proof, and change it so that the randomness used in the interactive proof is replaced by some output of a hash function that depends on the message. So if you want to do a signature, you will start from your message, do in your head or on the paper the interactive proof of knowledge, but you replace the randomness by the output of a hash function that depends on the message, and then you publish all the proof, all the protocol, and this is the signature depending on the message. And everyone can verify that the protocol is correct and that the verifier accepts the proof. And if it's the case, as you cannot cheat on the randomness, as the randomness is the output of a hash function, then it's a signature, and only someone knowing the secret is able to provide the signature. Okay. To show you maybe quickly what we can do with the decoding problem. So you have your secret E of weight R, and you have E H transpose equals the public syndrome. And you want to prove you know E. Of course, you don't want to show the value of E because it's your secret. So you will take at random a permutation and a random value. So you take a permutation, a random value, and you compute the new syndrome such that U plus E is has this syndrome. And of course, if you have the Hamming distance, so the weight of E is the number of non-zero coordinates. If you permute the coordinates, it's the same weight. And then you commit to 3 values that are, so committing to a value is giving the hash value of, it's computing the hash function on your value. And hash function has the property that you can not compute a pre-image of your hash function. So it's cryptographically impossible to compute a pre-image. So you send that to the verifier, and the verifier cannot recover all these values. But if you give to the verifier the value, he can compute the hash function and check that you add this value before. So you commit to all those values, and if you are able to compute all those values, it means that you know E, because if you don't, you cannot. So if you reveal all the values, you reveal the permutation, you reveal the permuted value of E plus U and of U, so you can just compute the permuted value of E. As you know P, you can compute E. So it's impossible to provide to commit to all these values if you don't know the secret. And then the verifier takes a random I and asks you to reveal all but one. Okay, and so you reveal all but one in each case, and then we check that the values you reveal are compatible with that, so that you really know E and take a random permutation and a random U. So for each of the questions, it's possible to cheat and to commit in advance to two values that will give a correct check without knowing the value of E. But you need to anticipate and know the question in advance. And if you are able to answer all the three questions, then you know the value of E. So the idea of the protocol is you run the protocol once, and you can cheat for two questions, but not for three. So you have 2/3. So you have two chances to succeed in the protocol among three. And then you do the protocol several times until it's... So the probability that you don't know E is very small if you can succeed in all the queries. So this is not a very efficient protocol, but it's the first one, the Stern protocol. And it allows to prove the knowledge of secrets. And it's very interesting because you use random instances of the decoding problem. And today I will take codes that have using a different metric. So it's called the rank metric. It was introduced by Delsart. And so it applies to codes where the length of the code is the product of two integers. And in this case, you have a vector of length m times n. You can see it as the coefficient of a matrix. You just take the coordinates and put them in a column way. And then you define the weight of a word to be the rank of the associated matrix. And it is a distance, like the Hamming distance, but a different one. So I have an example. You take this vector of length 20. So here I decide to take 20 as 4 by 5, and I put the coordinates in column. And so to some vector, you associate a matrix, and you can compute the rank of the matrix. Here it's clear that the last row is the sum of the three first rows. I work over F2. And also you have the identity matrix here, so the rank is 3. And so you can take linear codes just as before, but when you compute the closest vector, then you change the metric and use this rank metric. Of course, if you want, you can change the setting at the beginning and say 20 is 5 by 4, and I take different matrices, or you can put the coordinates by row instead of column. Or you do what you want. You first set the setting, and then you have a metric. And there is another way of defining this metric, is by using the isomorphism between the vectors of length n times m over fq and the vectors of length n over fq to the m, using the isomorphism between fq to the m, the vector space, and the finite field fq to the m. And how do you do that? You just fix a basis of fq to the m as a fq vector space. And then, so I fix the basis. And then you decide that vector of length n over fq to the m, it corresponds to a matrix where each row is the expansion in the fq to the m of an element in fq to the m. To show you exactly, I take a vector with coordinates that are in fq to the m, and then each coordinate, I expand it, I have a vector in the basis of fq to the m over fq. Okay, and it's exactly the same as before, but I have just taken a compact representation of vectors of length 4 over fq as element of fq to the 4. Okay, it's the same size if you want to represent the data. Just another way of thinking of this metric. And algebraically, you can recover your vector as the product of the matrix times the basis. And the rank is defined in the same way. And you can also define what is called the support of a vector, which is, so the coordinates of the vector belong to fq to the m. And you can look at the fq vector space generated by this coordinate. And so this is what is called the support. In the Hamming setting, the support is the position of non-zero coordinates. And here it is the vector space generated by the coordinate. It's also a basis of the column in the matrix setting. So here I have a support. And now we can just look at linear codes. And as I have vectors over fq, it's very natural to consider fq linear codes that are the codes defined by Delsart in the first place, and they're called matrix codes. And it's just a linear code as before, using the rank metric. But in the fq to the m setting, you can also look at particular codes that are fq to the m linear codes. And now you have a basis. So each row of the generator matrix represents a matrix in the matrix setting. But instead of just taking a multiple by elements over fq, you take also linear combination over fq to the m. So there are very specific matrix codes with a structure coming from the fq to the m linearity. And for this setting, what is interesting is that we have families of code with efficient decoding algorithm, which is not really the case for matrix codes. And the interest in cryptography is that using this fq to the m linearity, you save a factor m when you describe the public matrix. So you have shorter key for cryptography. So why is it? Because if you have equivalent codes, for matrix codes, the coefficients are in fq, here in fq to the m. So in fq, you have log q, the size to store a coefficient is log q, and here it's m log q. The length and dimension here are n and k, and if you want to describe the same amount of data in the matrix setting, then the length will be n times m, and the dimension will be k times m. And if you do the computation, you have a factor m here, which comes from the fact that to describe, so with one code word here, you describe q to the m different elements in the code, whereas here with one code word, you just describe q of them. So you have no relation between generators here, whereas you have some here in the setting. So it's really more interesting, and also you have efficient decoding algorithm for some family of codes. So we are interested in this decoding problem. So what is called the rank decoding problem is the decoding problem of linear code that are fq to the m in rank metric. Okay. So it's a classic decoding problem. I have a basis generator matrix of the code. I have one vector, one point that is at distance at most r from the code, and I want to find an error of rank at most r that correspond to this point. And you have the equivalent syndrome formulation, which is the same. And what is also interesting is to consider the decoding problem just for codes that are FQ linear, so matrix code. In this case, so your generator matrix is a matrix whose rows correspond to matrices. So you are given a generator matrix of your code, which is a set of k matrices, and another matrix corresponding to the vector you received, and you want to find an element in the code that is at rank at most r from the vector you have. Okay, and this is the min-rank problem, and maybe you know this problem from other application, but it's a classical problem in linear algebra. You are given matrices of size m by n over fq, and you want a linear combination of the matrices that has a small rank. And this is exactly the decoding problem for matrix code in rank metric. So what is the complexity of this problem? The min-rank problem is NP-complete. So doesn't mean any instance is easy, but in practice, if you take a random instance, then it's a hard instance. For the FQ to the M linear code, the decoding problem is easier in some sense. It's not clear it's NP-hard. There is this structure. There is a randomized reduction from the decoding problem in the Hamming metric to the rank decoding problem with some constraint, and it's a probabilistic reduction. And so there is no clear complexity result saying that rank decoding problem is NP-hard. And the min-rank problem is clearly harder than the rank decoding problem because it's a generic version, and the rank decoding problem is a specific case with a structure. Just to tell you, there are different schemes that has been submitted to the second call from the NIST for digital signatures that are RIDE, that is exactly based on the rank decoding problem with zero knowledge, proof of knowledge, and everything. And two of them, Mira and Merit, are based on the min-rank problem, again, in a random setting. So what I will present you today is an algebraic analysis of this problem. That is, how can we evaluate the complexity of solving the rank decoding problem or the min-rank problem. And this allows to fix parameters for these schemes to achieve some complexity. And it's also interesting to study the min-rank problem because it is used to cryptanalyze different schemes. For instance, in multivariate cryptography, there is also a new min-rank attack in the Hamming matrix on Machelis. I will not present it today. So, first I will just show you how we can use an hybrid approach on this problem. So I start with this decoding problem. I have, so it's for the rank decoding problem. I have this, so G and Y are public, and I want to find E that has a small rank. And finding a vector of small rank, you can write it as the product of S, which is a vector, which is a basis of the support of E. So S has a length R. It's unknown, but I can take a random. And C is the coordinates of E in the basis. And as the support, so the coordinates of E are generated in the FQ vector space of the support. The coordinates in the matrix C are in FQ, not in FQM. Okay, and we can do this remark if in the vector E I have A positions that are 0 by chance. Then it means that A colon in C are 0. Okay, because if I take a linear combination of a basis that is 0, then all the coordinates are 0. And if I have A coordinates that are 0 here, I get a linear equation in X. Okay, so I can rewrite my problem and reduce to a smaller instance where I remove A values in X, A colon in C, and I have a smaller problem with a new G, a new Y, where the length is still M, the field does not change. But I have N minus A columns in all the matrices, and the dimension here is smaller, it's K minus A. Okay, so if I can reduce to an instance where I have A positions that are 0, then I can solve a smaller problem. If I have this constraint, then I can do that in a deterministic way, just by multiplying here by an invertible matrix on the right to do elimination and put zeros at some here in some coordinates of E. I will not show you the matrix, but believe me, it's possible. If you have, you just need to know position in E that will be independent, and then you can like try all the possible combination, and you will at some point, you can do a proof that you will get zeros in E. So you can just try all the possible multiplication by a matrix, and among all of them, one will be really with zeros, and when you solve your system, your reduced system, you get the solution, and all the other one will not have zeros here. And so your hypothesis that the R position are 0 is wrong, and when you solve the system, you have no solution. But you can reduce to Q to the AR different systems, and among all of them, one has a solution and all the other has no solution. And if you do not have this constraint, then it will also work probabilistically. You can try several, you multiply by several matrices on the right, and then with probability 1 over q to the AR, you will get an instance with A values in E that are 0. And the
so q to the AR is not considered large?
It is large, but we want to design a system with complexity 2 to the 140. So it is large and it's good. But the interest in such a reduction is that you have an hybrid approach. Part of the attack will be combinatoric. So then you have this cost at the end. You have the combinatorial part of the attack, q to the AR, and then the cost of solving a smaller problem. What is interesting is that as you have a smaller problem, if the problem is very small, then you can do it in practice. And you are much closer to the good estimation of the final complexity if you can like run this small problem and then multiply by, we will end with the theoretical complexities estimates for this part. And so we can look for the best value of A such that the total complexity is the best one. And usually it's for large A so that this part we can just run it on a computer and check it. So okay. So now I come to the most important part of my talk, which is to design an algebraic modeling for the rank decoding problem. So I have this public matrix. I can compute easily a parity check matrix of the code plus this vector, which is a matrix that is orthogonal to G, the concatenation of G and Y. And the interest of such a matrix is that it will cancel all elements in G and Y. So first formulation is what I wrote before, is you are looking for E, which is xj plus Y, and the rank is small. But this is not algebraic. So, and I have the equivalent, it's not algebraic, and I have two sets of variables. I can just remove one set of variables by multiplying by this parity check matrix. And I have just one set of variables and this constraint that I want to write algebraically. And it's what I wrote before. You write that a vector has small rank if it is the product of two matrices of small rank. Okay, so here I write that E is the basis generating the support of E over FQ times the coordinates of E in this basis. Okay. And then I have an algebraic equation describing my problem. I just want to solve. So E is linear here, and I can just replace this value here. And I get a first modeling, which is I have two sets of variables. So maybe I can write it to keep it on the board. So I want to find and those are in F Q to the M. And here I have an R times N matrix. in FQ. Okay. So this first modeling was proposed by Oreski and Johansson. And so the question is, if you want to solve it, you compute the Gromner basis, how long will it take? And it's not easy to analyze the modeling because you have, so the degree can be huge and you have degree falls and you don't know what happened after the degree falls. So it's not easy to know how it will behave. So we propose another modeling that is, if you have this relation, then it means that this matrix, this one, has some elements in its left kernel. So this is a C by n minus k matrix. And if you have an element on the kernel on the smallest dimension, then it means that all the maximal minors of the matrix has a rank default, and you can write an algebraic system which is all the maximal minors of the matrix are 0. So it's another modeling, and I will try to explain why it is, in some sense, more interesting than this one, and why we can tell things about the complexity of solving this modeling. So if you look at first sight, you have minors. So the equations are of degree R in the values of C. You have a lot of variables, all the entries of C, and you also have a lot of solutions to this problem, because for any solution, if you multiply by an invertible matrix, then it is still a solution. Okay, so you have as many solutions as the number of invertible matrices, which is very large, and you clearly don't want a modeling with so many solutions. And also, one solution is enough. You don't want to find all the solutions because you know all the matrices here. So just want one. And also, any matrix of rank strictly less than R will be a solution. So you also want to remove this solution. So the idea is to make a bet that the first columns of C are independent. It will be the case if the first R coordinates in the error vector that you have generates is a basis of the support of the error. It's not always the case, but you have a random vector, you can compute the probability that it is the case, and you will try like several times, but with few tries, you will find R coordinates that are independent. And so if you know the first R coordinates are independent, then you multiply by an invertible matrix, and you can assume that you look for one C that has the identity here. Okay? And so now you just expect one solution to your system with such a C. You have less variables. You have just this number of variables. Still, you have equations of high degree. And here there is a magic trick, which is called the Cauchy-Binet formula. Here you have a minor, which is the determinant of a matrix. And your matrix is the product of two matrices. So you want to apply that the determinant of the product is the product of the determinants. Of course, you cannot do that directly because your matrices are not square. But you can do it's almost the same. It's an expanded formula. The determinant of a product of matrices that are non-square is the sum of the product of the determinant of submatrices, subsquare matrices. If you do that, you expand your polynomial as a sum like that. And what is very specific for this setting is that you don't have a mix between the two matrices. You have a product of terms that are minors of C times minors of a public matrix. So you can do a change of coordinates and use what is called the Plucker coordinates. So the problem we had is that there are a lot of matrices C that are solution to the problem, all the matrices that generate the same vector space. So you want coordinates that will describe a vector space. And this is exactly what is given by the Plucker coordinates. So the Plucker coordinates take a vector space and send it to a projective vector. So you take any generator matrix of your vector space and you send it to the vector of the minors of the generator matrix. And now if you have another generator matrix of the same vector space, then it is some A times this C. And on the image, you just multiply by determinant of A, the vector, so you get the same point in the projective space. So to one vector space through this vector, you have just one vector that describes exactly your vector space. So we do this change of coordinates, and now what we have is a system of equation. We have n choose R variables that are the minors, and the equations are linear. So that's very nice. We can just solve the linear system and get the solution. Okay. What is the problem? The problem is that we don't have enough equations to solve the system. And if we don't have enough equations, then what are all the solutions to the system? The problem is that we have two kinds of spurious solutions. The ones that are solution over the algebraic closure of FQ, because we never said the coordinates here have to be in FQ. And the coefficients of the linear equation are in FQ to the m. So by default, the vector space of solution is described over FQ to the m. And I just want the coordinates, the solutions that have all the coordinates in FQ. So if I don't add this constraint to the system, I will get a solution with some coordinate in FQ and some other in FQ to the m. And the second problem is that using the change of coordinate, I could get solutions that are in the image of the Plucker map here, but that are not, I could get solutions that are not in the image of the Plucker map, that are in this projective space, but that do not correspond to the evaluation of all minors of a matrix. So for the first problem, it's quite easy to solve it. I can just use the field equation. Using the field equation, if I'm working over F16, it's not so easy, but there is a nice way of doing that, is to unfold the system, the linear equation. I have equation with coefficient, so variable in FQ, but coefficient in FQ to the m, so I can apply the Frobenius morphism. And I will get, so when I apply the Frobenius morphism, I have a Q to the L power on the variable 2, but I use implicitly the field equation to replace that by the variable. And I get new linear equation because the coefficients now are different And so usually, for random instances, those equations are all linearly independent between them and from the initial one. Of course, you have instances where you have relation, but generically you have m times more independent equation here compared to the initial setting. For the second part, you can add algebraic constraints saying that you are in the image of the Plucker map, and those constraints are the relation between minors of a matrix. But so we did not succeed in this analysis, so we don't know how it behaves if you add this relation. So our system is now the system with all these linear equations expanded over FQ. And here I take the QS power, so I have coefficient in FQ to the m, but you can change it and get a linear combination with coefficient over FQ. So you have a system of this number of equations over FQ, and this number of unknowns that are all the minors. And if you have parameters with more equations than unknowns, then you solve the linear system, you have no spurious solution, and you get your solution just by solving a linear system, which can be quite large if the parameters are large, but you get a solution and a complexity estimate. If you do not have this condition, then you need to do something else. You can just use the hybrid approach. If you remember, it will change nk to n minus a and k minus a. So here you do not change the number of equations, but you reduce the number of variables. So at some point, if you specialize enough, large enough A, you will get a solution to your system. You can try adding the relation between the minors, but we did not try this this case. And so we also have another modeling that introduces another set of variables from the beginning. And I will try to explain this second modeling. So I start again from my equation here. So we remove the x variable by applying the parity check matrix, and then the s variable by taking the minors. And what we can do now is something different. So I will just present you the result, but if you analyze the system, in fact, the new equation can appear if you compute the Grosvenor basis of this system. At some point, you will get degree fold, and the equation produced after the degree fold are exactly the one I will show you. So the idea is you have a vector here that is a combination of the rows of this matrix. So you can just write a larger matrix with the C matrix here and this row here, and the rank of this matrix is just R, not R plus 1. So you take all the minors, all the maximal minors, and you write the equation saying they are all 0, and you should get a solution of the system. So it gives you this number of equations. The coefficients are over FQ to the m. And you have two sets of variables, the x variables and the c variables. And as it is, you have minors of a matrix, you can expand the minor along the first row, and you get linear polynomial combination with coefficients that are linear in x of minors of c. So you can still keep your Plucker coordinates for c. And if you do that, the equations here are bilinear in the x variable and the minors of c. So you have a bilinear system. Be careful, the c are in FQ, but the x variable are in the extension field. So you can say, it's cool, I know the complexity of solving a bilinear system, so I can just apply the complexity result. Of course, it's not a regular bilinear system because it's made of minors of a matrix, so there are relations between minors. And so we are interested in the complexity and the algebraic relations, the CZGs that are that we have between our equations. So we have these new equations, and we still have the previous equation. We can use them in our system. They are interesting because they are linear. And the question is, are they independent or not? In fact, they are not. It would be too easy. So I can separate the equations here. So each equation is indexed by a set of column coordinates where it takes a minor. So I take a set of r plus 1 coordinates between 1 and n. And I'm interested in the number of coordinates that belong to the first k plus 1 columns. And using that, we have a proof that if you take the minors with I that belong to the coordinate k plus 2 to n, so you avoid the minors that have a component in the first k plus 1 coordinate, then these equations are contained in the vector space generated by the others. Another thing that we can prove is that the equation P are in fact also contained in the other equation. And we have a one-to-one correspondence between the equation in Q1 that are equations having just one column in the first k plus 1 coordinates, and the equation in P and the multiple of the equation in P by a variable x. So we can do exactly the proof of the correspondence, which means if we want to add this equation to this one, in fact, we lose all the equations in Q0 and Q1. They are linearly dependent. And what is nice is that the equation in P, the multiple of the equation in P by x and the equation in Q2 and larger, we can prove that they are linearly independent. And we can do more. We can describe all the Macaulay matrices in higher degree for this system. Just to give you a hint of why we have this result, all the relations come from specific minors. Here, for instance, I have the matrix of my Q equation, and if I multiply by this parity check matrix, then the first row is 0, so it's clear that the minor is 0. And this is why the equation in Q0 reduces to 0. For the other proof, we have to introduce monomial ordering, and we can prove that the leading term of the linear equation are the sub-minors of C for the indices that belong to k plus 2 up to n. And the leading terms of the equation in Q, we can write them exactly, and the leading coefficient is 1. So as soon as we can prove that, we have a proof that they are all independent and that And we can describe all the Macaulay matrices in higher degree. And in fact, the Macaulay matrices are already in systematic form. Okay. This is also another relation proving that the P equation are in correspondence with the equation in Q1, but I will not give you the details. So at the end, we have two sets of equations. For all those equations, we can describe exactly the leading term for a specific monomial ordering. The equation in Pj start with this variable, and this variable appears nowhere here. So we can just eliminate them and then analyze the equation here. We have a description of the leading term for all the equations, so we can describe the Macaulay matrices that are already in Lestrade form, and we know all the space of solution. And of course, if we can prove all of that, it means that we have a large number of solutions, and we can never, so we have too many solutions in the system, and we can never reach a point where we have more rows than columns in the Macaulay matrix. So we need something else. In fact, again, we forgot to add the constraint that the C variables are searched in FQ. So we can eliminate much more C variables by unfolding the linear equation, just as before. And when we do that, we lose the proof we have of independence. Of course, because at some point, there are relations between the equations because you have too many equations. So the system we propose is the set of Q equations here and the linear equation unfolded. So we analyze what's going on when you remove C variables using the linear equation and plug it here. And when you do that, there are CZGs to the system, again, that come from minors. But we can analyze them. So the linear CZGs come from the application of the Frobenius on the previous system. So believe me, you have this relation, and this gives you a relation between the equation at some higher degree. But if you take all of that, look at it carefully and compute, so you can compute the number of CZGs. It's not so easy because you have CZGs but relation between the CZGs, so you need to compute everything. And at the end, you get formula that are, it's the only terrible slide, I hope. But you can count the number of monomial at in the matrices. So we look at Macaulay matrices in B degree, some B in X and just one in C. So the number of monomial is the number of monomial of degree B in X times the number of monomial in C where you have removed the number of linear equations you have. So this is exactly the number of columns of your Macaulay matrix at B degree B1. This is the number of rows you have when you put the Q equation in your Macaulay matrix multiplied by some X. And this is the number of CZGs you have when you remove all the C variables using the linear equation. And so we call regular systems that have no other CZGs than this one. And in practice, if you start from a random instance, then your system is regular, and we can analyze the complexity of solving the system at some B degree. This is when you have the rank of the matrix is larger than the number of columns, and you have an estimation using linear algebra of the number of operations you need to solve the system. So we can then estimate the complexity for the concrete parameters for new for the submission to the NIST competition. So these are the parameters for the right crypto system, the first security level. So here you have the rank of the target rank, the rank of the error that is your secret. Here you have the log of the complexity, and I put, so in blue, you have the complexity of the max-minor approach, which is the linear system, where I use the hybrid approach to be able to solve the system. So for the small values, you don't need an hybrid approach. You just have enough equation to solve, so you have a very efficient algorithm. And then you need to have a slope that is that follows the combinatorial part of the complexity. So this increases. You have here the slope for the best combinatorial attacks. So you see that when the rank is large, we are worse than the best combinatorial attack because our hybrid attack is just naive combinatorial attack time efficient algebraic approach. So when all the complexity concentrates on the algebraic and the combinatorial part, as we are not efficient, it's clear that we will be worse. And we have this support minors approach that is not more efficient than the max minor approach here, because we have to introduce another set of variables compared to the max minor approach, and this has a cost. And here we are over F2, and the combinatorial part is small, it's very efficient. So it's not so interesting here. The approach with just the linear system works very well. And so for the right crypto system, for the right signature scheme submitted to the NIST, we choose the maximal possible values for R, so the security level is very high. And here I plot the part of the combinatorial approach in the hybrid approach. So this is the value of A we need to choose in order to be able to solve the system. This is the, so for max minors it's the smallest A, and for support minors we try different A, compute the maximal degree to solve the system, and take the best result. And so you see for small values we don't need any A, so in this case it's very efficient to solve, and then A grows up to the maxi, a complete combinatorial attack. And what is interesting is that our resolution is not dependent of the size of the finite field. So when the field is larger, then our attack becomes more efficient compared to combinatorial attacks. Because the Q to the AR part grows with Q, and the other part, the only change is the linear algebra over FQ, but it's not a big part. So in this setting, we are always better than the combinatorial attack, and the support minors become more interesting than max minors approach, because you can take a smaller value of A, which is here. You can see here that, of course, you need a smaller value of A to be able to solve the support minors approach with more variables than the max minors approach. Okay, do you have questions?
Not on that slide, one of the previous ones, you have this one. What is this DRGV?
It's the weight of the error. the maximal weight of the error that you can take if you want almost one solution to your problem. And if you are below that, you expect one solution. So you expect exactly one solution when you are below half of the minimum distance. But if you are after that, you have few solutions to your system. So you can go further if you still have one solution. And here, at some point, you go from few solutions to an exponential number of solutions. So you stay just before, and you expect just one solution or like two solutions, but it's not much. Yes?
Okay. Related to this question, how problematic is it not to have just one solution? I mean, for in cryptography.
It's not a problem because here, in most cases, we will have an hybrid approach. So in the hybrid approach, you specialize at least one variable. And like if you have few solutions, and you specialize one variable, you will get just one solution. So it's really not a problem. And if you want to find exactly all the solutions, then instead of computing just the last Macaulay matrix and taking an element in the kernel, maybe you need to compute all the Macaulay matrices to have a Grobner basis. But so if you compute the kernel of the Macaulay matrix, you will get the vector space generated by all the evaluation of the solution. So if you have two solutions, it's still manageable. You can search in this vector space all the possible values and then solve. Or you compute the entire Grobner basis, but the cost is not so much larger because the maximal cost is the last matrix. But if you are in a hybrid setting, you have no problem. You just have one solution. And so I also add the modelings for the mean rank problem. Maybe I can just show you quickly what are the modeling. So you have this problem with K matrices, and you want to find a linear combination that has a small rank. You take the parameters such that you have 0 or 1 solution, because that's what you want for cryptography. If you have 0 or 1 solution in the algebraic closure, it means you have no spurious solution in the extension field. So you don't need to add the field equation. You may want to add them over a very small field. Before, we did not add the field equation because the field is not F2, it's F2 to the M. Now we have a FQ, so it's interesting to add square equation, quadratic equations. And so what are the different modeling for this problem? The first one is Kipnis and Shamir modeling. You take your matrix, that is a matrix with entries that are linear form in the X variable. And you look for a kernel of dimension at least n minus r, which means the rank of the matrix is at most r. And you can solve the system. You have a bilinear system that is not regular, not bilinear regular. You have another modeling, which is a matrix has rank at most r if all minors of degree r plus 1 are 0. And this modeling is very well understood. There is all this work from Jean-Charles Moab and Pierre-Jean that analyze exactly the CZGs of the system, the size of the Macaulay matrices, the relation between the rows, and we have we know all the Hilbert series, the maximal degree. We can compute the complexity of solving the system. One drawback of this system is that you have just to compute the equations that are minor. So you had the talk from Vincent with the complexity of computing minors of a matrix with entries that are polynomial, linear polynomial, but polynomial. So it's not so easy. And we have another modeling that is like the support minors modeling. And it's just, the idea is here you have a description of dual code of this matrix, if you think in terms of code. So this matrix is orthogonal to this code. The dual code is this one, so you can just say any row of this matrix belongs to this code. So you write a matrix with this unknown and one row of the M matrix, and you compute all the maximal minors, and you have a lot of equations. Here, what is interesting is that you can again use the Plucker coordinates, and you have bilinear equations. And we can also do the analysis, compute the CZGs, and provide a complexity estimate. And nowadays, if you want to use the min-rank problem to design a crypto system, you take the parameters so that all the complexities are the same. And what is nice also is that if you take this equation or this equation, in fact, they generate the same ideal. So without the Plucker change of coordinates, but if you don't change the coordinates, you have exactly two systems describing the same ideal. Just the complexity of solving the system is not the same. And here, understanding the complexity of solving this system is not easy because you can just take your system, compute the Grobner basis, look at what the behavior of the Grobner basis, and for most of the parameters, it will grow up to degree r+2. And in degree r+2, what you find is a lot of degree folds, and you produce all the minors equation, and you produce all the support minors equation. So it seems that this is not the best idea to start from this system and to run a Grobner basis. It's better to start from this one or this one. And again, if you start from this one, at degree r+2, you will have degree folds that are exactly those equations. So, okay, so in conclusion, algebraic cryptanalysis can be a very powerful tool. It really depends on the algebraic modeling you can write for your system. With different algebraic modeling, even if it describes the same ideal, you have different behavior for the complexity. For each new system, you need to do again the analysis, design a new specific algorithm, and I don't know. So people ask me all the time, do you have a way of doing that automatically for any system? I don't know a way of doing that. So for each system, you need to look at it again, experiment, understand the CZGs, compute the rank of the Macaulay matrices, and get a complexity result. So thank you for listening. Do you have questions?
Any questions?
That's one.
On the slide just before, I think. No, not this one. Yeah. You say that what's the most efficient to compute in the better attack on the minor is the last one, the best modeling?
It depends on your parameters.
What do you mean on the MI?
It depends on the the values M,
Okay.
R, N, etc.
Okay, so
For some parameters, this modeling is better. For others, this one is better. And sometimes in this modeling, you have degree falls at very low degree, and you can do something better. So it depends.
Okay, and we have no.
But so the interest of this modeling is the fact that you don't work with polynomials of degree R or R+1. You just start with polynomials of degree 2. But for the parameters we take for cryptography, at the end, you need to compute the Gromov basis up to some large degree, and you get equations that are of the same degree as the equation you will get in this modeling when you try to solve it for the same parameters.
Okay, and since it depends on the parameter, is it possible to predict for which parameter which modeling is better?
Because you have a complete analysis for both modeling.
Okay.
So you just take your parameters, compute the complexity of solving the both modeling with the results that are known, and take the best one.
Okay.
Yeah. At the moment, so there are 2 submissions to the NIST competition that are based on random min-rank instances, and for both submissions, the complexity of solving with both modelings and with the combinatorial attacks are on the same level. The parameters are designed for that.
Other questions? So I have perhaps another question. The complexity analysis which is done, does it include the case of possible quantum computation?
No. You can do that in the hybrid setting. So some people do that. I'm really not specialist of quantum computation, so I don't know where is it. Yeah, here. Here you have an hybrid attack with parts of combinatorial part and a part which is solving an algebraic system. So some people say I can use a quantum computer to run this part faster, but I really don't do quantum computing, so it's only classical analysis here.
No more questions, so thank you, Magali.